Thank you very much, Aviv and Amit and Mario for invitation and for organization of this wonderful meeting. I think it's really amazing. I'm enjoying it very much. And today I would like to tell you a little bit about our research, how we are trying to improve the specificity and the sensitivity of biomarkers for iron in context of neurodegenerative diseases. And this is members of my group, so Shear's image appears here again. And our goal is to try to develop methods which would be sensitive to the cellular, so to have some cellular specificity. Because I think looking at the talk today in the morning, we have heard a lot about different cell types. We have heard a lot about different molecular imaging and the component where the iron can be bound. And in MRI, you very often have just these regional measures. So the conventional MRI is sensitive and quantitative tool, as Karin and Aviv have shown, and it's perfect to give us the measures of iron on the macro scale, on the regional level, which is already great. Advances in high-field MRI give us, first of all, much better sensitivity to iron, but also allow us to resolve much smaller structures. And this specificity to mesoscopic scale, to brain nuclei, may be actually very important, and as I will show you in the context of substantia nigra. But what we would fundamentally want to know, actually, is to distribution of iron at the cellular level, and that's very difficult to achieve with MRI, and not just because of the sensitivity or limited time available for measurements on the live patient, but also because of the fundamental limitation of the diffusion on the time of the experiment. And then I think what would be really interesting is to have at least some molecular specificity, as has been shown in many talks. And this is where actually biophysical models of MRI signal can be helpful, because if we would be able to precisely understand how the MRI signals, different MRI parameters reflect iron in different cells or in different molecular bound form, then we could perhaps push the boundary of what MRI can reveal. And I think Aviv have shown a very nice example of it. So why can we do so? It's because iron, so we mostly look at water, right, in MRI in most cases, but the water interact with different microscopic components of the tissue, such as iron or macromolecules, at very different scales and very different temporal and spatial scales. And Aviv have talked about T1, which is sensitive to very quick fluctuation and a very local interaction. And I will talk mostly about the T2 star measurements, which actually reflect magnetic microstructure of the tissue. So the T2 star reflects the heterogeneity of the tissue at the microscopic scale. Let me see if the slide advances.
Yeah, it gets stuck once in a while.
Let's see.
Here it is. Here it is.
Oh,
Here.
you just was too far. Okay.
Yeah.
Right. So I will quickly show you that, as I mentioned, MRI is sensitive but not very specific tool. And what can we do in order to move towards the in vivo histology by ultra-high field MRI? And there I kind of move through the very small scale, looking at the signal neuron. Then I go to the voxel, then to the nuclei, and then, if the times allow, I will also show you something about the evolution of the brain imaging accumulation, where we compared between human and great apes. So MRI is sensitive and it's quantitative. I think that's a great properties of this metrics, and it's actually outperformed histology in many ways due to this quantitative nature. And it has been shown by the comparison between the MRI measures and histological measure in cadaver brain that there is a nice correlation between the bulk susceptibility, for example, shown here, and iron concentration, or for R2 star and also myelin and iron content. So it's kind of sensitive. However, this is a model just reflect the total iron, so we doesn't know where it's located in, and it's really important to. Oops. Oh, I think it's stuck again. Oh. So, and the idea here is that the different cells. So how does the R2 star come? What is the physics behind R2 star? You can think about iron-rich cells actually as a tiny inclusions, so tiny small dipoles in the tissue. And if you put them into magnetic field, they generate this dipole field around them. So the spins located close to the pole or close to the equator would experience different magnetic field. They dephase, and this is how the signal decay. And what's very important is that there are two contributions. One is the static one, depending on when spin is located, and the second is a dynamic one. So if the spins start to wander around those cells, it leads to the fluctuation, the temporal fluctuation, and it causes T2. So there is these two different contributions, and they really depend on how big the cells are, how far they are from each other, and how much iron do they have. So it gives us physically the opportunity to distinguish different cellular distribution. And that's exactly the effect I wanted to explore. So what we are doing using the in vivo MRI with a very high resolution, combine it with the postmortem MRI on the postmortem tissue, because there we can do first increase the resolution very strongly, and secondly we can do advanced quantification of the tissue and then find out the ground truth. So we can really know with the cellular specificity how much iron is distributed. We then can use it to calculate all the magnetic field in our voxel, predict magnetic parameters, validate the model, and then apply it back to interpret the in vivo data. So I just wanted to show you why all these methods are important here. And then we heard that several times, but I wanted to repeat it, that concerning the molecular specificity. So we have heard about this really important function iron has in the brain. So it's kind of really good. But we also heard that there is this evil part on it. But actually, in the most of the case, sorry, oops, my joke is gone. Because actually what the most of the iron is, right? And the tragic thing is that we have, the only tiny finest part is harmful, 20% is useful, and that's actually the most is the passive one. And that's what we want to know, but that's what we measure with MRI. So let's face the fact. So the question is, can we do something about it? And I think a little bit we can learn, because we can use the fact that there is a chemical equilibrium between these different forms. So partly we may infer from this passive one something about the in vivo one. And I'll show you one example. It would be really interesting what you think about it. So for the rest of my talk, I wanted to give you one example, walk you through one example, and that's the early detection of neuronal loss in Parkinson's disease. And actually, David already asking the question actually give a fantastic introduction, because it has been recognized 100 years ago in Sorbonne that the loss of the dark pigmented neurons in substantia nigra in the tiny nuclei causes motor symptoms in Parkinson's disease. So there has been an epidemic of Parkinson, probably followed by the Hispanic flu. It's not quite known. And so they looked at many cases and realized that this motor symptoms comes with the loss of these tiny, tiny, tiny cells. Later, there has been a very detailed work by Damier et al. Who cartography the distribution of cell loss across the nigra and find out, first of all, that these cells groups in tiny clouds called nigrosome, and they defined 5 of them. And that the biggest nigrosome, so-called nigrosome 1, shown here, degenerate most and the earliest. And the tragic part, and I think David already described it, that at the moment where we have motor symptoms, 75% of the cells are already gone. So it's really difficult to do any curative treatment. So any imaging which would be able to detect this loss early before, that would be really a game changer. So again, this was presented very nicely by Hamid already. So why do this? So the special thing about this neuron that they're very dark and they're extremely iron-rich. So it's probably one of the iron-richest cells in the brain, definitely. I'm not sure how they compare with erythrocytes. So the reason is because they need iron for synthesis of dopamine, and they are, I think, the heavy lifter in the brain. So the most of the dopamine are produced in those cells. So they need it in the tyrosine hydroxylase to create dopamine, but unfortunately, there is an auto-oxidation of dopamine in the presence of iron, so it creates a lot of very harmful species. And there is a process in these neurons which they developed in order to make it less harmful. So they kind of polymerize it, put it in the vesicles, and store it in this waste polymer neuromelanin. And this is extremely dark, unsolvable substance which make them darker and darker in course of their life, and has enormous amount of iron in it. So you can think about neuromelanin as a sponge, having at least two different places where the iron can be stored. And they are very different, first of all, in terms of the magnetic property, but also in terms of the dissociation constant. So this more neuroprotective binding site is antiferromagnetically coupled, very, very, very safely stored iron. And then there is the other one, which I called here neurotoxic because it's less bound, and it has a much higher magnetic property, which is interesting for MRI, but is also dissociate much easier. So if we now think about the chemical equilibrium and write the equation for the chemical equilibrium between the two, and we'll calculate what would be the concentration of two binding sites depending on the saturation of neuromelanin with iron, what will happen that in the beginning, the high bound, so safe store will be saturated, and then the low affinity will start to saturate. And here I also calculated the amount of labile iron, which is exaggerated by 1,000. But what you see that unless the first one is not saturated, everything is very good, then the thing's becoming a bit worse, and then the amount of iron really strongly increase. So actually, this is kind of, this lazy guy, and here's the dangerous one, but interestingly, you can infer the amount of, dangerous iron based on the ratio between the two. And that's interesting because the red low affinity iron is much more magnetic. So the susceptibility of neuromelanin increases together with its toxicity. Right. So it's a current view. The idea is that the dopaminergic neurons get older and older. They try to compensate. They get more and more neuromelanin. At a certain point, it's too much. They get oversaturated with iron. They get too much oxidative stress and start to die. And getting this time point would be really, really nice, just to know where they are. So any non-invasive monitoring methods would be very, very welcome here. So there are powerful neuroimaging markers, as we have seen. First of all, increase of iron has been reported, and so we was talking about it. However, this marker is unspecific, and I'll show you a little bit why I think it's the case. And the second marker was the so-called swallowtail. So in the healthy substantia nigra, you would have a tiny bright spot, and it disappears in Parkinson. So it's already great, so it's a big promise, but it's still qualitative. So any quantitative marker would be great. And here I wanted to show you some data which we acquired together with our colleagues in Paul Flechsig Institute in Leipzig, with whom together we developed a method how to specifically measure cellular concentration in different cell types. So what we do, we slice the tissue, and then we do immunohistochemistry enhanced by nickel. So the compartment of interest is now stained with the nickel. And then we perform our measurement of iron with a very high resolution, either with the proton-induced X-ray emission or with X-ray fluorescence. Now we can mark the cells in the nickel map because we map all metals, and then specifically measure the iron concentration inside of this compartment. So in this way, we can really try to disentangle this increased iron concentration into the different cells. And when we compared the Parkinson and control shown here in gray and pink, we see that actually in all cells, the iron is enhanced. It is particularly strongly enhanced in the neurons, which is probably the primary process, but it's also strongly increased in oligodendrocyte and microglia, which may reflect all the secondary processes, and that's definitely in two different chemical forms. So if we interpret neuroimaging marker or construct new, it would be really interesting to tackle this process differently. And now I'll show you what we have done. So that's a task. So can we try to detect the loss of the cells in vivo? And we started, with a single neuron. And that's actually the PhD of very talented student Marta Bramelo, which I'll tell you now. So here you see the MRI microscopy on the postmortem tissue of in substantia nigra, recorded with a 22 micrometer resolution at a very, very high field. And what you see, these tiny, tiny, tiny dots, they actually correspond to the location of dopaminergic neurons. So if we would have this high resolution, we would be able just to count those, because neuromelanin acts as a natural contrast agent in these cells. And if you look at the frequency distribution around those, so that's QSM basically, you also see these tiny dots with the paramagnetic iron. So now we used, now it's slowly again, just a second. Okay. So now we can think about, we can build a model. We can think about which individual centers have been a tiny iron-rich sphere, creating the dipole around it. And from the physics, we know that the dipole is proportional to the susceptibility of the metal, amount of metal, and proportional to the magnetic field. We can now invert this relationship. Let's see. We can invert this relationship, right? It's really hard. So I hope you get the same, the same answer, right? So now, let's see, and now the great thing that we can measure this dipole field with MRI microscopy, actually using the method Karin presented you, but on this micro scale. And we can, if you would find the same cell, we can measure the metal concentration with the X-ray fluorescence. And that's exactly what we have done. Right, and the next cell, you see again, the magnitude and the phase, and here's the zoom into the one particular phase. And to create determine this, dipole field, we have to do a little bit of biophysics, because it's not a usual situation with MRI. Usually we have, big object, we have tiny voxels much smaller than the object, and then we have the diffusion length of the water much smaller than the voxel. And here we have the cell, which is much smaller than the voxel, and the diffusion is comparable with the voxel size. And so it's kind of, it's not, okay, right. So, but we can fit the effects. So here it's a simulated response that's an experiment, and determine this magnetic moment for the cell group, then slice the tissue and find exactly the same cell. So it sounds easy, it's not that easy, but we found, we have done it. So thanks to Maite's persistent. And, I have to build too many animation in my slides. So, okay, right now, you see the experiment. Now we can fit the line through that and determine the susceptibility finally. And I think it's really nice method, because it is a measurement of the susceptibility of iron without prior isolation from the tissue. It's very important because isolation can change the state of iron. It has a sensitivity of picogram per cell, and can work on the big, large ensembles. This is particularly important if you want to compare with MRI. And we actually perform very well compared to other methods, because we work at the room temperature and can cover really big tissue.
How do you calibrate that?
We calibrate it in the two ways. First of all, we calibrate our iron measurements, because they are calibrated with the standard and also from the first principle. And so for the iron measurements are calibrated with the or there is a first principle calculation. We actually compared also two different methods, PIXI and XRF, and they compared very well. Right. And I think we already can learn a lot from this value, because if we compare it with the two values for the two sides, we see that the equilibrium is actually already very strongly shifted to the low affinity binding sites, and maybe actually indicate that at this samples, which was aged individuals, one should say, it's already in the direction of saturating the neuromelanin. So it may explain the contribution of iron to explain to pathology, particularly in those cell types. Right, so we are actually, I wanted to show you where the, if I'm back, no. So you have to believe me. So basically we were on the bottom upper part of this top, right. Now I want to go from the single neuron. So now we understood the single neurons want to move to the single voxel. So that's a difficult problem, okay, because now we have, of course, much more. In one voxel we have hundreds of cells, and we have to, theoretically solve this problem by integrating over the all possible configuration the cell can take. Right. So what we performed here, we did we mapped all the cells in the one voxel, created the model, and then compared the performance of the model, the analytical model shown here in the red. The black is the Monte Carlo simulation, and the brown is the experiment. So you see that they compare quite well. So we were using here one very specific model suggested actually also for bolt imaging by Dmitry Yablonsky in the 90s, who showed that in the case of many, many small perturbers, we can describe the relaxation rate as a product of number of perturbers, number of cells, and multiply by the amount of iron in each cell. So actually, this means that by using the susceptibility values we determined in the previous experiment, we can now obtain the product of the cellular load multiplied by the volume fraction. So it's kind of a meaningful value which we can extract from our experiments. So, but remember that the theory is valid, especially in the nigrosomes, in the tiny nigrosomes. Now I wanted to move from single nuclei to try to apply it in the radiological science interpretation. And when we start to do it, we faced the fact that actually our interpretation and our model, also it worked very nice, actually contradicted completely the common view. Because the people thought that the nigrosome is the same as this bright tail in the substantia nigra. And our model predicted that due to the presence of many, many cells, it should be really dark. And we've seen it in postmortem tissue. So it's not just some mismatch, it's kind of completely opposite. So as a physicist, you always believe your theory, and since you don't know neuroanatomy anyway. So we looked, and the other thing is we looked at the literature, and we find out that it's extremely challenging because the structures we are talking about are really, really tiny. So the size of the nigra is the size of the bean. The swallowtail is much smaller. So when you co-align them, histology and MRI, you have to be extremely precise. And the study, the interpretation from radiology was based on one single study, very carefully done. But we thought, okay, it's really easy to make a mistake here. So what we have done, we used our collaboration with a group of Birte Forsman in Amsterdam, where we acquired the 3D multimodal data set. And that's a data set where we had several brains, which we scanned with MRI with a multimodal approach, very high resolution, so 400 micrometer resolution. And after that, this brain went through the 3D histology with a very different staining. So we could use Kalbinding histochemistry to really localize nigrosome in this data set. And here you see another data set, which is acquired in the even, so it's to celebrate the high resolution. Exactly. Thank you very much. And so
works at least.
So you can compare actually nigrosome with the layers in the cortex, so because they're as small, and with this resolution of 300 micrometer, you can see them, and you see the nigrosome in this MRI. So what we have done we have, and that's exactly was done during the pandemic, where we can't go to the lab, so it was a perfect time, to coloring data set. So we used the histologist Markus Morawski. He segmented all the nigrosomes. And Penny Goland, who was the first author actually on this publication, original publication on the swallowtail, she segmented the swallowtail. And then we co-aligned the data sets before, and like the MRIs. And then when we got the registration, we put them on top of each other. And what we can see, you can see it in the, and this was done on the 3 brains. Oops, sorry. So that in all of them, the swallowtail and the nigrosome co-aligned by only partly. And they had a very different shape. And actually, nigrosome goes in the middle of the swallowtail. So if you want, they relate to each other as the bread and the sausage. They come together often, but they're not the same. So you have to be very careful when you look at this really precise structures. You also need to be anatomically very precise. Right. And now, as a byproduct, we actually created this nigrosome atlas, which we're going to release very soon. And this can be used probably even for the analysis of the data set, for example, Arthur-Starr data set, even acquired with a lower resolution, because you can focus on the subpart of the nigra where really the neuron sits. Right. So now, at the next step, we would really like to apply this in vivo. And we have got funding from GPND research funds, where we apply it in the cohort across different 7 Tesla sites. Actually, Stefan Licheritzi is also part of that, where we're going to apply these methods in the cohort of healthy control, de novo PD, and patients at risk of PD, and then follow them across actually 2 years to see if we detect the degeneration. So for that, we need very, very high resolution MRI. And we use a multiparametric MRI at 600 resolution. We also have the prospective motion correction as an option. So actually, probably not all sites will use that. But I show it because I think it's the interesting development done in the neurophysics department. And that's actually the Karen Pine who developed the methods. There is a tiny holographic center attached with a bar clip to the patient. And you can follow the heartbeat and the breathing and correct them in the real time. So you get even better results. And here's some data set which Karen recorded for this data with our colleagues in Liège. What you get is all the different contrasts. So R1, R2 star, QSM, PD at once. And we can now use that for segmentation of the different brain areas and also for assignment of the integrity of them. So here you see the maps and the overview. We also have a T2 measurement following actually the approach Noam developed, so also dictionary-based T2 measurement. So it unfortunately takes too long yet to do whole brain, so we focus on the Nigro region. So I think it will be a really nice data set. And the great thing is that if you use different contrasts, they are perfect to segment subcortical regions. So the classical R1 or MPRH, it's not enough to see precisely delineation of the nuclei because subcortical anatomy is so complex. But our colleagues in Amsterdam, they developed a method which is called a MASP algorithm. It's a multiparametric automated segmentation of subcortical regions developed by Pierre Bassin in Amsterdam. So it runs, it eats multiparametric data and automatically segments your region, so you can look at regional effects much more precisely. Right. And with that, I would be at the end of my human research, but would I have some time, or is it? No, okay, good. Otherwise, I would have shown you some monkey data. Then with that, I would like to thank my colleagues. And so just to say you a little bit that, of course, a lot of the postmortem research are done on the brain of humans, and they are normally aged. So you want to change already, or because this? Yeah, go ahead. Okay, and okay, and And it's very difficult to look at neuromelanin accumulation in mice because they're just too short. And we are very lucky to have a chimpanzee data set on chimpanzees where we do a very similar experiment and also can follow the saturation of neuromelanin over ages. But I don't not have time to talk about it.